We're live. Oh, excellent. So thank you so much for joining us, David, Professor Gross, Professor Maldacena, and Professor Page. It's fantastic to have you here, and really appreciate you joining and giving your time to do this interview and debate and discussion. So our audience is probably going to be mostly native Russian speakers, so it's a good idea to remember to give some good volume and to speak slowly. So I'm with the beginning. Let's start off at the beginning and talk about the beginning of the universe, the Big Bang. A wonderful question that a lot of people will have is, how did it all begin, and what happened before the Big Bang? So I'd like to know how you guys like to answer this question. Maybe we can start with you, Professor Gross.
So are we on now?
Yeah, I believe we're totally live. Yeah. Although we may have a small delay, little hiccup here. Perhaps Professor Maldacena is active.
So I'm active, but are we on now? Are we?
Yes, we are live now. That's what I've been told, yeah.
Very good.
Can you yeah. Check. Check. Yeah, Professor Gross, you can answer. Can you go ahead and start if you would like to answer this question? What happened before the Big Bang?
Well, that's one of the deep questions that we're trying to probe. The theorists among us are trying to do it with pencil and paper, and my good friend Lyman is trying to find signals that might inform us as to what happened at the beginning. But if the question was what happened before the Big Bang, where space-time began in some sense, personally, I don't think we yet have the right way of thinking about this. Somehow the deep questions in physics often require new ideas, new formulations in order to ask the question correctly. So the very fact that it's so hard to answer a question like, what happened before the beginning of time, suggests that our notions of time especially are inadequate currently to even ask the question correctly, much less answer it. Many of us think that we're going to have to seriously modify the way we think about space and time in certain extreme conditions, and the beginning of the universe is certainly one of those. So I think the honest answer is we have no idea. There's some interesting proposals, but this is, one of the main and most difficult questions that physics is facing. That's not an answer.
Yeah. It's a very fair answer. It's
we don't know enough to even ask the question correctly.
Yeah, I think the important thing to realize is that our current theories fail at the beginning of the Big Bang. So the theories themselves tell us that they are failing. And so we need a theory that goes beyond the ones we have today. The main difficulty is to find a theory that puts together quantum mechanics, so the physics that we use to describe atoms and so on, with space-time, the physics we use to describe the universe, the structure of space-time itself. So...
I mean, Einstein's biggest revolution 100 years ago was to teach us that space and time are dynamical objects. And although he didn't like it also quantum mechanical objects. And we haven't completely absorbed what that means. It most likely changes the way we think about space and time.
I mean, even though we don't know exactly what this theory is and what exactly happened at the beginning, we can say something about what happened a little bit afterwards, after the beginning. So there's a nice theory called the theory of inflation that tells us what happened just a little bit after. And it has a little bit of the elements that we expect that are necessary to answer the previous question. And one of the elements is the fact that time itself has some quantum fluctuations. There's a certain uncertainty in the flow of time. And these uncertainties are amplified by this phenomenon of expansion and inflation and so on, and are things that are currently being explored directly experimentally by Lyman and friends through the observations in the cosmic microwave background.
Yeah, can we hear from Professor Page? Can you chime in maybe?
Oh, I'd be happy to. What Juan and David are referring to are these measurements of the cosmic microwave background, this faint radiation left over from the Big Bang that surrounds us, if you will. And in this model of inflation that David mentioned, in many versions of it, not all, but in many versions of it, there should be gravitational waves left over from the Big Bang. And these waves should leave a distinctive imprint on the polarization of the microwave background. So not only are we looking at this radiation as you would with, say, normal glasses on, but we're looking at this radiation with polarized sunglasses on to look for tiny variations in the polarization that would tell us about the possible presence of these primordial gravitational waves.
And how far back could we get to with the information from primordial gravitational waves? To what period of time after time zero? It's going to be, and David and Juan can correct me, about 10 to the minus 33, 10 to the minus 35 seconds. So that's a billionth of a billionth of a billionth and a little more of a second. Pretty good.
The radiation that we're looking at really comes to us from about 380,000 years after the Big Bang. But the imprint from this primordial, from the primordial gravitational waves is put in is put into the radiation at 380,000 years.
Okay, great. It's really nice. Okay, so let's maybe I can ask a little bit more like a lighthearted question. I know that pretty much a universal question that I get asked and everybody wants to know, and it would be great to know from the top echelon of experts, is there your views on the life in the cosmos? You know, what do you think? Are there aliens? Can you just shed your opinion, your view on life in the cosmos?
Well, we're here. That's the one bit.
Besides the
So one bit of direct evidence we have for life in the universe. And given what we know about chemistry, biology, physics, the structure of the universe, it seems extremely unlikely that we're alone. Fermi famously asked, well, if that's so, where are they? What is really exciting nowadays is that we are looking very hard and also have been listening for many years unsuccessfully for signs of life. But now we can actually observe planets similar to our own. And we hope to be, my friends, astronomers, hope to measure the composition of, chemical composition of the atmosphere, which could easily show signs for life. In fact, there's some evidence recently that there might be life in the higher atmosphere of Venus, which is very close by.
Yeah.
I expect that we will, in the lifetime of many of the observers of this discussion, observe some form of life in our galaxy. However, whether we'll observe intelligent life that we could communicate with, it seems to be much more of an open question.
That's fair. What are your thoughts, Professor Maldacena?
Yeah, I think this prospect of looking at other planets and their atmospheres is really interesting, and I think it's quite likely that there is cellular life or some, this basic kind of life that we had on Earth for billions and billions of years. Intelligent life occurred only in a very small fraction of that time. So
you're optimistic on life. Are you optimistic on intelligent life?
That seems to be a much harder proposition. Probably not.
If you look at us as an example of intelligent life, you might get worried that intelligent life.
Yeah, that's fair.
Itself in a very short time, and that might be the answer to Fermi's question: where are they? Why can't we talk to them if they're all over the galaxy? It could very well be that species like ours that develop language, science, technology inevitably destroy themselves. We seem to be, unfortunately, there are signs that we might be moving in such a direction.
Mm-hmm. Yeah.
Maybe add a little perspective there. The center of the galaxy is 25,000 light years away. So say we have been able to seriously communicate for 100 years, right? If we had sent out a signal, it would not have gotten to many places. So one of the challenges is that the universe is enormous. It's huge. So we can observe well, and I think we're all very excited about the prospects of seeing forms of life, but to see an advanced society, we'd have to be very lucky.
Mm-hmm. All right. So perhaps I can preface this next question with, the atmosphere of 2020 has been full of fear. There's been a lot of crazy ongoings in this year in particular. And well, with respect to the cosmos, maybe I can get your view on what do you think is humanity's biggest fear with respect to what should we fear about the cosmos? A lot of, you might get a lot of people saying that we should fear black holes or gamma rays or asteroids. So what are your thoughts on this? What should we fear today about the cosmos?
I think we should fear nothing. There are more practical problems. Care not, and we should take care of the earth, take care of our political systems, our economic systems. Those are more important things. And
it's a question of probabilities and timescales. So we've learned that there could be events happening on an astronomical scale that affect us. In fact, we believe that many of our species on Earth were wiped out by meteors or comets, and close by supernova would do a lot of harm. But the time scales are so much larger than the time scale of human history and of our lives that we need to put that in perspective. The time scales of what we're doing to our planets and to ourselves is
order.
Perhaps unfortunately very short.
Mm-hmm.
Yeah, and just maybe to add to, I would, when you look up the sky, I think, awe and beauty should be what comes to your mind.
No fear, no fear.
No fear. It's beautiful, and we keep making measurements, and so we can we learn it better and better, and it's and deeper, and it's just increasingly interesting.
Yeah, it's a nice change of pace to have this cosmological perspective of awe and beauty, and mystery. Okay. Leading into that, then, do you feel, Professor Page, do you feel like humanity will survive into the far future, and on, say, cosmological time?
Oh, cosmological time is a tough one. I would say I am hopeful. We will evolve and we change, and from a cosmic perspective, we have barely been around. So who knows? I'm sure life will evolve in some way. I mean, we see complex molecules deep out in space. So life will evolve. Whether species like ours will be here.
Well,
who knows? I hope so.
If we survive, it won't be we for sure, since we've learned that life continues to evolve and change. So we're just a stage in the development of life on this planet. Inevitably, we, in some way or another, and we might hurry this up rapidly with our new knowledge, evolve into, something else. Who knows? By the way, you started the program by asking about the beginning of the universe, the Big Bang. From the point of view of physics, where the laws of physics are symmetric with respect to reversing the direction of time, an equally interesting question is how will it end?
Yeah.
And that's another question with great mystery attached to it. If you ask how the universe will end, or will it end, the answer is, again, we don't know. And it's perhaps as difficult a question as how did the universe begin?
Yeah, and that has a factor to play in the survival, or whatever kind of imaginable survival you might have of the humanity. Yeah, sure. So, do you feel that, or what, considering the evidence that you're familiar with, what's a likely scenario, do you think, how the universe will end? I mean, besides, it's obviously clear no one knows for certain, but perhaps you have an intuition or in any kind of inkling.
There are many bad scenarios.
Yeah, it's all bad.
Well, I think you have to put this.
They're either bad or boring.
Yeah.
So, it could be boring, but at least not a big crunch or a big rip. But we don't really know. Mm-hmm. But we can, the kind of measurements that Lyman Page is doing will inform us about that. For example, we've learned that the universe is filled with what we call dark energy, sort of the energy present in the vacuum of space, and that causes a rapid expansion of the universe. And if that energy is non-diminishing, the universe will continue to expand and be a either very lonely or disastrous place in the far future. But we're not sure about that, and we can get information from the kind of observations that Professor Page carries out. So we can learn about the future.
But this has to be put in perspective. We are talking about cosmic timescales, where the progress of science could also tell us how to deal with this. So some scenario which now sounds boring or disastrous, maybe we'll be able to learn from it. We will be able to learn how to deal with it through the tools of science.
Right. It's hard to imagine us affecting the structure on cosmological scales of the universe, but who knows?
Yeah. So is it true then, Professor Page, that your measurements and the data you're familiar with then gives a lot of evidence, or at least a strong possibility, is the big freeze, where it's a very boring far end for the universe? Is that a basic consensus of the evidence?
Yes, if you take the elements of the models, if you take the evidence that we have now and the model we currently have, the universe just continues to expand and empty out, if you will. So that's the big freeze you're talking about. But we don't know if we're actually quite certain that there are elements of this model that are missing. This model has, in cosmic time, has not been around that long. It fits the data very well, but we're looking for departures, and in 100 years, who knows what we might find? We'll certainly find something else. But if you were to say right now, it would the best bet would be the big freeze that you spoke of.
Okay, great. So perhaps on a more positive note than the end of the universe, we might suggest an exciting discovery in cosmology, maybe a most exciting discovery that would just really make you feel great. What would that be?
Oh, I can tell you. I mean, it would be really neat to see gravitational waves left over from the Big Bang, and to maybe put this in more recent some perspective. As you may recall, a few years ago, the LIGO experiment and now the LIGO and Virgo experiments measured gravitational waves on Earth from inspiraling black holes, inspiraling and coalescing black holes. And that was, a stunning, beautiful, careful, and difficult measurement. If there are these waves left over from the Big Bang, they'll be a million times stronger, if you will, but also very, very difficult to detect, and with much longer wavelengths and much slower variation. So that would be a beautiful thing to find, and many of us in the community are trying to do that. And to give you another idea there, although the model we have of the universe is backed up really well by the data, there is evidence that even growing evidence that we really don't have all the pieces just right. We might It might be there's something wrong with some of the measurements, but we're starting to get to know things so well that we can look for departures from our baseline. And we're all excited about what you might see. You just push the measurements a little more, you do a little better. As the history of science, you do better at making these measurements, and you see something new that just changes the way you think about the universe. And it seems like that could be right around the corner, and it's another thing that just keeps us going.
Yeah, that's great.
Yeah, the other perhaps reasonable hope in the short run for a discovery that could change our view of the universe is to figure out what the dark matter that pervades the universe is made out of. That we know that the universe has a lot of matter that we can't see directly, just feel its gravitational pull, and we don't know what it's made out of. We've been searching for that for decades now. It could be discovered tomorrow, but that is sort of a guaranteed great discovery around the corner, which will affect our understanding of matter, our understanding of elementary particles and the forces of nature, and to be sure of cosmology, since most of matter in the universe is made of this dark matter.
Mm-hmm. Yeah, that's clearly 72% of the universe is is dark energy, so maybe 72% of all the physics departments should be studying this.
Very hard to study dark energy, believe me, experiment.
Yeah.
It has almost no effect except to push the universe into an expansion.
Professor Maldacena, what about you? What kind of discovery in cosmology would?
Yeah, I think the two that they mentioned are the most important ones. But I think now there are new techniques. The most important thing is that new techniques are being developed to look at the universe in a new way. So one is the discovery of gravitational waves that LIGO is detecting, and this will give us a new view and maybe show us the existence of objects that we didn't dream about. Another possibility I find exciting is something involving another form of radiation, some hydrogen emission line that could give us also some information about the primordial fluctuations. It's similar to what Lyman is observing, but it will give us a full three-dimensional view of the universe and will let us characterize the primordial fluctuations much better and see what was going on during that time. So that's another window into the very early universe.
Yeah, I like that. Actually, I've just gotten a question from the audience, which I think it would be really nice to engage with the audience here. They've asked, how soon will we populate Mars? And is there such a need? Is there such a need for this? And it would be interesting to know from the Elon Musk cult is very prominently support this idea, but it would be nice to know from a physicist point of view, about more short-term exploration into the cosmos, say Mars. So what do you think?
Personally, I'm not interested in going to Mars.
Oh, yeah?
It would be nice to send some better robots there, but it's of course achievable by humanity. We have the technological means of doing so. It's not clear what benefit that brings. However, in the long run, if we look at cosmological times, and intelligent life like us survives a few thousand, maybe the order of 10,000 years, it's very reasonable that we will populate the galaxy. Not we, but our DNA or our information that will establish life throughout the galaxy. So we'll send out spores, robots with bits of information and robotic ability to create life on other planets, that can lead to us life emerging from us or developing from us, populating the galaxy in millions of years for sure. That assumes that we survive on this planet for 10,000 or so years, which is somewhat questionable.
I see. I like the, from a scientific perspective, I think it's good to remember that there may not be so much to learn about cosmology or fundamental physics by having a colony on Mars, but certainly, I guess other areas of science would benefit.
Yeah, the back of the moon would be a nice place to have a telescope, but.
Yeah, definitely. Perhaps I can get the opinions of Professor Maldacena about Mars. What do you should we go there
Mars
soon?
is very inhospitable. I mean, it's easier to live in Antarctica than to live in Mars. And
It's easier to live on Antarctica.
Yeah, much easier. Yeah, much easier. And
Okay.
there are very few people that go to Antarctica. And spend a amount of time. Maybe they go for a year, perhaps.
Yeah, so baby steps first. So you might say we should get good at living on Antarctica before we colonize.
But I think Mars exploration is interesting. It's interesting to know whether there was life on Mars, what the conditions are on Mars. And it teaches us about the Earth, the solar system, and these are very interesting questions. And it's likely that these are being explored with robots, with cheaper robots that you don't have to bring back. And yeah, they're teaching us a lot about Mars currently.
Okay. Professor Page, would you live on Mars?
Well, I can say I lived in the Antarctic for a year, so I know that's possible.
That was a practice.
Yeah, that was practice. Oh, I'm glad people are thinking about it and thinking about how to do it. My preference is much more along the lines of what David and Juan were saying too. For finite resources, we could learn much more with robots, and we'd learn more how to work in space, and just even how to assemble things in space. There's much more to be done with robotic systems. I'd say before tackling all the hurdles of getting humans there.
Great. So, well, let me maybe ask a question that I would love to know, to pick your minds, is when it comes to cherished fundamental principles of physics. It'd be just kind of fun to know what you feel is your most cherished principle of physics, be it say the action principle or causality or second law or Lorentz invariance or what have you. What comes to mind as maybe the most quote unquote sacred?
Nothing is sacred in physics.
Of course.
Everything is open for question. And the most interesting, what I find as the most interesting principles are the ones that are most questioned nowadays. So at the bottom of our understanding of nature now is quantum mechanics, which is still rather new, only less than 100 years old, and we're still somewhat confused sometimes about quantum mechanics, especially when applied to the dynamics of space and time. So from my point of view, those principles of quantum mechanics are the most sacred, but also the most questioned nowadays.
Cool. So like, for instance, you might boil it down to the Heisenberg uncertainty principle or duality and wave particle duality and these quantum principles. Is that
well, it's not so much those. It's to a large extent we we understand quantum mechanics very well in situations that we've applied it to, structure of atoms and the structure of matter. But applying quantum mechanics to the structure of space and time is something which can be very confusing. We're learning a lot about it, theoretically. And it relates to the questions you asked at the beginning about the origin of the universe. So there is a place where some of our most sacred principles are being questioned. And it's not that we're going to have to throw them away, but understand them much more deeply.
Mm-hmm. Right. Professor Maldacena.
I particularly like the second law. So the second law
is probability theory. It's not a law really of physics.
Yes. But I think it is a law of physics in the sense that we experience it every day. And it's related to one important mystery, which is why the universe started simple and gets complicated in the future. And I think a deeper, perhaps, understanding of how to apply the second law to the full universe is very important and confusing. So,
Einstein once remarked that the second law of thermodynamics are a statistical theory of systems with many components, and the increase of entropy, et cetera, that defines an hour of time that Juan was alluding to, is the one principle in physics that will never be altered. And to some extent, it's because it rests on the law of large numbers. It has sort of a mathematical foundation that transcends all realizations in particular physical theories. But as Juan remarked, why did the universe begin in a state of low entropy and is now time as defined by the second law is a deep mystery related to how the universe began again. We keep coming back to the origin that you.
Yeah, and important. Cool. Great. So there's a current conflict, I understand, in cosmology with the Hubble constant, measuring it appropriately. Do you have any thoughts on how this is going to fall or where this is going to end up?
Sure. So just to make sure we're all on the same page, right? If you measure the Hubble constant by looking at the cosmic microwave background, you get one value. If you measure it by looking at nearby objects, and nearby are millions and millions and millions of light years away, you get a different value. What that means in more practical terms is if we measure the expansion of the rate of the universe nearby, we get a different value than we would infer by measuring it from looking at the edge of the universe. So the question is this a hint that our simple model is missing a new element? And I think that's the most exciting outcome. I think we're all sort of hoping for that this is a new handle on something in the universe, but it's at least in my opinion, it's too early to go to that. These are very difficult measurements. There are, for the microwave background, at least two different groups with independent data agree on the value. You can't say that quite as solidly for the nearby measurements yet. There's some difference. And I should also add the nearby measurements are more challenging. because the universe today, the nearby universe, is much more complicated than the early universe, and much more difficult to take apart and to understand all the possible systematic effects. So really very interesting. It's one of those clear cases where more measurements are needed. And we are maybe on the verge of discovering a whole new element of the universe that we didn't know about 10 or 20 years ago. So exciting, and
yeah, some new physics perhaps.
Yep.
That's great.
Yeah.
Okay, so perhaps maybe we can ask about final theory. Is there a final theory? Is that like asking, is there a final song or a final painting? Or do you think that it is possible to unify quantum theory and general relativity into one framework? What do you think?
Well, my opinion, I have no doubt that it is possible to unify quantum mechanics and gravity. We're well on the way to do that. But a final theory, but you know, once you answer these difficult questions that are posed today, like quantum mechanics and gravity, the history of physics is that you find new questions that we hadn't even thought of before. So certainly historically, there's never been a period where we run out of new questions to ask. And as to whether we'll ever run out of such questions and have a final theory, I'm very agnostic. It could be that that somewhat like the exploration of the Earth will run out of the Earth is round and compact, and there's only a finite amount of area to explore. But it could be that the Earth of knowledge is flat, and we'll just go on one will need to go on forever. There is no limit to our exploration. I don't think we have any reason to believe in either picture. And certainly the evidence so far is that as successful as we tend to be in developing explanation of the phenomena we've so far explored, we always find new phenomena and new questions to ask.
Well, I'm interested why you're so confident that quantum theory can be unified with general relativity. You have no doubts.
Because both of these elements of our current understanding of nature are well tested. Mm-hmm. And, you know, you can even make an argument, but I won't really try to at this point, that the fluctuations that Professor Page measures in the cosmic microwave background are caused by quantum fluctuations of the space-time, by gravity waves that are consequence of quantum fluctuations of gravity. And although, you know, that's not as direct a test as you might want, it's totally convincing to us theorists. And but in addition, just to the fact that, you know, these are two pillars of our current understanding of cosmology, of gravity, and of the other forces of nature, we're making enormous progress towards clearing up the difficulties in combining them. So personally, I think, you know, we're well on the way to clearing up that problem completely.
Yeah. That's great. Professor Maldacena, are you on the same page with that there'll be no problems that will eventually unify quantum theory and general relativity?
Well, I think this is a problem that's been left off from last century, from the 20th century. So we learned two aspects of nature. One is quantum mechanics, the other is space-time and general relativity. And they, as we currently understand them, they are not consistent. They're not mathematically consistent. And this inconsistency shows up when you try to look at what happened in the beginning of the Big Bang or in the interior of black holes. So that's why we are confident that some theory should exist. There should be, nature knows what to do, and there should be some theory. The theory, whatever it is, should reduce to quantum mechanics and should reduce to gravity. And so I think it somehow follows from logic that, and from the assumption that nature is described by logic, that there should be such a theory. And we are exploring various possibilities. We are trying to construct theories of this kind, and I think we have some interesting candidates that we're exploring. And I hope before soon we'll be able to understand it completely. I don't see why not.
Cool, but it won't be a final theory though. In your what about your view on that?
Well, final theory, it's just depends on exactly what you mean. I mean, here it's a very concrete problem. It sounds just to put together quantum mechanics and general relativity. Maybe after you do that, you can ask another problem, like where this theory came from and what the initial conditions were. I don't know. There could be new questions, as David was saying, and I think that's true. And also, it's a final theory for this problem of combining these two aspects of physics. Of course, this final theory will not tell you what will happen in the stock market or, many other problems in physics, biology, etc. So you should view it a problem in fundamental physics of understanding the very basic building blocks of nature. What are the atoms of space-time? Space-time is dynamical, like a membrane that can fluctuate. What are its basic building blocks? That's the question we're asking.
Okay.
I think we are in a situation similar to the situation in the 19th century when people thought that there might be atoms, but no one had seen an atom. They knew from indirect arguments like the existence of surface tension and so on. They had an estimate of the size of an atom. But it was really only in the 20th century that we had more direct evidence of atoms, and you could really take an atom, pull it apart, etc., and understand the structure of an atom.
That's true. It's a good analogy. Great. Okay. Maybe I can get your opinion, Professor Page, on a unified theory, maybe as an observational cosmologist.
Yeah, sure. Well, I like to measure things, of course. Let me instead just maybe give you a picture to keep in mind, building on what Professor Gross said, that the idea, these are measurements, right, of this light at the edge of the universe, these tiny variations in temperature that are big. We see them now. You can, if you could have microwave eyes, you would look up and see a sky with these mottled patterns in it. So very large patterns. And there's this connection that as we understand things in our model, that those are fundamentally quantum mechanical processes. They're results of quantum mechanics acting in the early universe and evolving in a universe governed by the general theory of relativity. And those fluctuations eventually, they gave rise to galaxies and clusters of galaxies and ultimately planets and us, right? So there's this, and as my colleague said, right, we're all here. We're pulling apart the pieces a little more each passing decade, and so from a experimental side, I'm hopeful, and very fortunate to have such smart theoretical colleagues working on pulling these things together.
That's great. Yeah, totally. Okay, so let me open up the floor to questions to each other. I think maybe since we're all here in the same internet room, we might just take a chance to, if you have any questions that you'd like to ask one another, that be it very abstract opinion or even technical, whatever you like. Anything that comes to mind.
I would like to ask Lyman his opinion on the prospects of seeing this 21 centimeter lines of hydrogen that could give us this new picture of the universe. So
No more questions. Okay.
3 dimensions. Picture of the universe.
Sure. It's a very difficult measurement because there's so much background. And it's a measurement that I think will happen. It will just take a long time and to get right. And it will, it's not as, I don't think it will ever be as clean as the cosmic microwave background. But it's too early to say that with confidence. That's obviously maybe a bias because I work in that field. We've got to look. There might be ways of looking at this radiation where we can extract more information than we think we can right now. Maybe that's I don't know if that quite answers it. It's a very difficult measurement, but we know we learn more. In 20 years, we could have, with advanced computation, we could have ways of picking apart the spectrum and zeroing in on just the right part that gives us insights into the universe. So I would strongly supportive of pursuing it. I just wouldn't put my money on learning something in the next 5 years, say.
Cool. Any other questions for each other?
I was going to ask Lyman also about the Hubble constant, but he answered that already. So.
Yeah.
Cool. Good.
But I have a question. What would be a measurement that, say, LIGO could make that would be most relevant for understanding black holes at a new level?
The black holes that LIGO is observing are very well described by classical general relativity.
Mm-hmm.
So any deviation from general relativity would be an incredible signal. We would have to develop a new theory. So I would think that that's probably the most interesting one, surprising one. It would be very interesting for learning something new about space-time. I suspect unlikely, but very unlikely. But that's maybe my theoretical prejudice.
Maybe some small mass black holes.
Yeah. Well, but very small.
Yeah, like
Earth size won't do. Yeah, one would need. It would be lovely if we could create black holes and particle accelerators, which were very small and very short-lived. That would totally revolutionize the way we study quantum gravity, but one should never rule out these possibilities, because anything we think of, nature might be amenable to. So people are exploring possible deviations from classical general relativity in LIGO observations, But I think, as Juan said, it's extremely unlikely, but should always be looked for. And the same is true with producing black holes in accelerator. It's extremely unlikely, but boy, would it be a great discovery.
Another fun possibility is that there could be tiny microscopic magnetically charged black holes that could survive from the beginning of the Big Bang. And that's one of the...
Magnetic monopoles.
Yeah, well, magnetic monopoles or even magnetically charged black holes, and any of them, either magnetic monopoles or these black holes would really allow us to explore nature at very short distances. Yeah, there again, somewhat unlikely. But,
yes, unfortunately.
This is interesting because these objects, we think they can exist according to the laws of nature. We think that magnetic monopoles can exist, magnetically charged black holes can exist, but it's hard to produce them. So it's hard for nature to produce them at the beginning of the Big Bang, but they are very definite predictions of our pictures for space-time and
right. And I think Juan would agree that we believe that there definitely are magnetic monopoles in the universe. In fact, one of the motivations that led to the theory of inflation, that the universe is expanding, that expanded very rapidly at the beginning, was to dilute the monopole content of the universe because we hadn't been able to observe monopoles. So that explanation makes a lot of sense. It does a lot of inflation, gets rid of a lot of defects that we don't see, but it also explains why it's very unlikely that we're ever going to be able to find these monopoles in abundance.
Yeah, that's actually that reminds me of a good question to ask. Is that and as I understand, magnetic monopoles make the equations very beautiful. And so, therefore, you might say this is a good argument for, a good bet that they exist, at least in part. But how do you feel about beauty affecting, scientific enterprise? Do you think that beauty can lead physics astray, or do you think generally, beauty is a good thing for physics, or essential even? What would be your I'd imagine that you feel that beauty is absolutely essential then.
I think the main thing is consistency, mathematical equations. Beauty is a bit in the eye of the beholder. So normally we call consistent equations beautiful, but I think the real important principle is mathematical consistency, which is just logic, that the theory makes sense. The magnetic monopoles are not
more than beauty is a human thing. I believe we have evolved to try, to understand nature, and when we understand something, we find it beautiful. That's the reward that our mind gives us for understanding. So when we refer to something as beautiful in mathematics or in the mathematical formulation of physical principles, what we really mean is, as Juan said, that it holds together and is a powerful idea or picture or description that has many explanations, that has much power. So I think it's not at all surprising that our explanations and our descriptions of nature are what we call beautiful. We've evolved to find them beautiful.
So with respect to the magnetic monopoles, the reason you're so confident that they exist despite no experimental evidence yet is based on logical consistency, you would say, rather than beauty?
No. We have theories. We have very successful theory called the Standard Model and generalizations of that, which the theories predict monopoles. They don't predict how many, they also predict often that these monopoles are extremely heavy. And that's why they're not produced when we smash particles together in accelerators. And in an inflationary universe, they could have been very abundant at the beginning when the universe was very hot and energetic and small. But then as the universe expands and cools off, they can't be produced anymore, and the expansion of the universe dilutes them. So it all makes sense within our present understanding. But but I think the reason we believe that they're very likely to exist is that they're almost inevitable consequence of the kinds of theories that are very successful in describing the forces and particles we do observe.
Okay, that's fair. Yeah. Okay, great. Cool. Okay, so I think it's about time, and I think that we've gotten the questions from the audience. So at this point, I'd like to wrap it up and give my thanks to Professors Gross, Professor Maldacena, and Professor Page. Thank you so much for giving your time, and it's been a pleasure to hear your views and your opinions and to learn a little bit about science this evening. So thank you so much.
Okay,
Well, thank you.
Thank you. It was a pleasure. Yeah.
Would have been nicer to be in Kazakhstan.
Yeah, absolutely. Yes.
We'll welcome you here. Maybe at some point, say maybe within the next few years, we might be able to have you here and fly you out in person. It'd be great.
Well, I look forward to it.
Yes. No, me too.
Cool. All right. Take care.
Good.
Stay healthy.
Yeah.